In the vast expanse of our solar system lies Mercury, the smallest and innermost planet orbiting our Sun. Often overlooked, Mercury captivates astronomers and stargazers alike. Its rapid orbit challenges our understanding of planetary formation. Mercury's significance extends beyond its physical attributes. As the closest planet to the Sun, it offers a unique laboratory to study solar radiation. By studying Mercury, we gain insights into our solar system. Mercury has shaped human history and culture. From ancient myths to modern science, Mercury captivates our imagination. Its story is intertwined with our quest to understand the cosmos. The name Mercury speaks volumes about its impact on human culture. In Roman mythology, Mercury was the fleet-footed messenger of the gods. This captures Mercury's swift celestial dance around the Sun. Ancient astronomers recognized its unique nature and named it accordingly. This connection highlights the profound impact celestial objects had on human understanding. Mercury's orbit around the Sun is a captivating spectacle, a celestial ballet governed by gravity and planetary motion. Unlike Earth's circular orbit, Mercury's path is highly elliptical, resembling an elongated oval. This eccentricity is the greatest among all the planets in our solar system. Mercury's distance from the Sun varies dramatically, from 29 million miles to 43 million miles. This fluctuating distance causes extreme temperature variations and shapes its surface. Mercury's orbital speed varies throughout its journey. According to Kepler's laws, Mercury travels fastest when closest to the Sun and slows down as it moves farther away. This dynamic interplay creates a complex and fascinating orbital dance. For centuries, Mercury remained an enigma, its small size and proximity to the Sun making it a challenging target for Earth-based telescopes. The glare from our star often obscured our view, limiting our understanding of this intriguing world. However, the advent of space exploration in the 20th century ushered in a new era of discovery, allowing us to peer beyond the limitations of Earth's atmosphere and unravel the mysteries shrouded within Mercury's enigmatic landscape. In 1974, NASA's Mariner 10 spacecraft made history as the first human-made object to reach Mercury, capturing the first close-up images of the planet's surface and revolutionizing our understanding of this celestial neighbor. The images beamed back to Earth revealed a world scarred by countless craters, a testament to billions of years of bombardment by asteroids and comets. Building upon Mariner 10's groundbreaking mission, NASA's Messenger spacecraft embarked on an even more ambitious journey in 2004. After a 7-year voyage that involved multiple flybys of Earth, Venus, and Mercury itself, Messenger entered orbit around Mercury in 2011, becoming the first spacecraft to do so. From orbit, Messenger revealed a world both familiar and alien, its surface bearing striking similarities to our own moon, while harboring unique features that hinted at a complex and dynamic geological history. Craters of all sizes pockmarked the landscape, some ancient and eroded, others remarkably well preserved, their sharp rims and towering walls casting long shadows across the desolate terrain. Beneath Mercury's heavily cratered surface lies a surprisingly large iron core, a discovery that has puzzled scientists for decades. This massive core, accounting for over 80% of the planet's radius, is proportionally much larger than that of any other terrestrial planet in our solar system, including Earth. Its presence has profound implications for our understanding of Mercury's formation and evolution. One prevailing theory suggests that Mercury may have once been a much larger planet, perhaps twice its current size, that experienced a catastrophic collision early in its history. This impact, according to the theory, stripped away much of Mercury's outer layers, leaving behind its dense iron core and a relatively thin mantle. Another theory proposes that Mercury formed in the intense heat and radiation of the early solar system's inner regions, where high temperatures may have prevented lighter elements from condensing alongside the heavier iron, leading to the formation of its massive core. Regardless of its origin, Mercury's oversized core plays a significant role in shaping the planet's magnetic field and influencing its interaction with the solar wind. As the closest planet to the Sun, Mercury experiences a range of environmental extremes unmatched anywhere else in our solar system. Its proximity to our star subjects it to intense solar radiation levels and extreme temperature fluctuations that would make life as we know it impossible. On the sun-baked surface of Mercury, temperatures can soar to a scorching 800 degrees Fahrenheit or 430 degrees Celsius during the day, hot enough to melt lead. This intense heat is due to the sun's proximity and the lack of a substantial atmosphere to regulate temperatures. Conversely, Mercury's long nights, lasting for 88 Earth days, bring about frigid temperatures that plummet to -290 degrees Fahrenheit or -180 degrees Celsius. This dramatic temperature swing between day and night is the most extreme of any planet in our solar system, a consequence of Mercury's slow rotation and its lack of an insulating atmosphere to trap heat. Mercury's unique position in the solar system and its elliptical orbit result in a peculiar dance between its days and years, creating a celestial rhythm unlike any other planet. While Earth completes one rotation on its axis every 24 hours, Mercury's rotation is much slower, taking approximately 59 Earth days to spin once on its axis. This slow rotation, combined with Mercury's rapid 88-day orbit around the Sun, creates a phenomenon known as a 3-to-2 spin-orbit resonance. This means that for every 3 orbits Mercury completes around the Sun, it rotates on its axis exactly twice. As a result of this resonance, a single day on Mercury from sunrise to sunrise lasts for 176 Earth days, twice the length of its 88-day year. Imagine a day that lasts longer than a year. That's the reality on Mercury, a planet where time seems to flow at a different pace. This unusual relationship between Mercury's rotation and orbit has profound implications for the planet's surface temperatures, its magnetic field, and its interaction with the solar wind. Unlike Earth with its life-sustaining atmosphere, Mercury possesses a tenuous and highly variable exosphere, more akin to a thin veil of gas than a true atmosphere. This exosphere is constantly being replenished by particles blasted from its surface by solar wind and micrometeoroid impacts. The composition of Mercury's exosphere is a fascinating mix of elements including sodium, potassium, calcium, and magnesium. These elements, released from the surface through various processes, create a faint glow around the planet, visible in certain wavelengths of light. This tenuous exosphere offers little protection from the harsh radiation of the Sun, or from the constant bombardment of micrometeoroids. It does, however, interact with the solar wind, creating a faint magnetotail that extends away from the planet, much like a comet's tail. The study of Mercury's exosphere provides valuable insights into the processes that govern the interaction between a planet's surface, its magnetic field, and the solar wind. Mercury's proximity to the Sun, a mere 36 million miles at its closest approach, subjects it to a level of solar radiation unimaginable on Earth. The Sun, a giant ball of burning plasma, bathes Mercury in a constant stream of energy, creating a world of extreme temperatures and intense radiation. Imagine standing on Mercury's surface at perihelion, the point in its orbit where it is closest to the Sun. The Sun would dominate the sky, appearing 3 times larger and more than 10 times brighter than it does from Earth. The heat would be unbearable, reaching a staggering 800 degrees Fahrenheit, hot enough to melt lead. This intense heat is due to several factors. First, Mercury's close proximity to the Sun means it receives a much higher flux of solar energy than Earth. Second, Mercury's slow rotation, combined with its lack of a substantial atmosphere, means that the same side of the planet faces the Sun for extended periods, allowing the surface to heat up to extreme temperatures. The intense heat generated by the Sun has a profound impact on Mercury's surface, shaping its landscape over billions of years. The relentless bombardment of solar radiation, coupled with the extreme temperature swings between day and night, creates a dynamic environment where rocks expand, contract, and even vaporize. The most striking feature of Mercury's surface is its abundance of craters, evidence of a long history of impacts from asteroids, comets, and other celestial debris. These craters, ranging in size from small, bowl-shaped depressions to vast impact basins hundreds of miles across, are a testament to the chaotic early solar system when collisions were commonplace. But Mercury's surface is not just a static record of past impacts. Volcanic activity has also played a significant role in shaping the planet's landscape. Vast plains of smooth volcanic material, evidence of ancient lava flows, cover large portions of Mercury's surface, suggesting a period of intense volcanic activity early in its history. Despite its proximity to the Sun and its scorching surface temperatures, Mercury harbors a surprising secret ice. Yes, you read that right, ice. This seemingly paradoxical discovery has puzzled scientists for decades, and has sparked intense curiosity about the nature of this enigmatic planet. The first hints of ice on Mercury came from radar observations in the early 1990s, which revealed highly reflective patches near the planet's poles. These reflective areas, scientists hypothesized, could be ice deposits hidden within permanently shadowed craters, where temperatures remain perpetually below freezing. In 2011, NASA's Messenger spacecraft confirmed the presence of water ice on Mercury. Using its laser altimeter and neutron spectrometer, Messenger detected the signature of water ice in permanently shadowed craters near the planet's poles. These craters, shielded from the sun's direct rays, act as cold traps, preserving the ice for billions of years. Another intriguing aspect of Mercury is its magnetic field, a discovery that surprised scientists when it was first detected by the Mariner 10 spacecraft in the 1970s. Although much weaker than Earth's magnetic field, Mercury's field is significant, extending far enough into space to interact with the solar wind. The presence of a magnetic field on Mercury is puzzling because it was initially thought that only planets with molten cores and relatively fast rotations could generate magnetic fields. Mercury, with its slow rotation and relatively small size, was not expected to have a global magnetic field. The prevailing theory is that Mercury's magnetic field is generated by the motion of its liquid iron core, which is thought to be at least partially molten even today, billions of years after the planet's formation. The exact mechanism by which this molten core generates a magnetic field is still not fully understood, but it likely involves complex interactions between the core's rotation, convection currents within the liquid iron, and the planet's overall rotation. Mercury's proximity to the Sun also means that it is constantly bombarded by the solar wind, a stream of charged particles constantly flowing outward from the Sun's upper atmosphere. This solar wind, consisting primarily of protons, electrons, and alpha particles, carries with it the Sun's magnetic field, creating a vast bubble around the solar system known as the heliosphere. As the solar wind flows past Mercury, it interacts with the planet's magnetic field, compressing it on the sunward side and stretching it into a long tail on the opposite side. This interaction creates a dynamic environment where charged particles from the solar wind are funneled toward Mercury's poles, creating auroras similar to those seen on Earth. The solar wind also strips away atoms and molecules from Mercury's tenuous exosphere, creating a faint tail of neutral particles that trails behind the planet. This process, known as sputtering, contributes to the evolution of Mercury's surface and atmosphere over time. The study of Mercury, despite its alien nature, provides valuable insights into the formation and evolution of planets, including our own. By studying Mercury's unique characteristics, such as its oversized core, its tenuous exosphere, and its interaction with the solar wind, scientists can gain a better understanding of the processes that shape the inner solar system. Mercury's proximity to the Sun makes it an ideal laboratory for studying the effects of space weathering, the process by which solar radiation and micrometeoroid impacts alter the surface of airless bodies. By analyzing the composition and structure of Mercury's surface, scientists can learn about the long-term effects of space weathering on other airless bodies in the solar system, such as the Moon and asteroids. Furthermore, Mercury's unusual spin-orbit resonance and its dynamic magnetic field offer clues about the planet's internal structure and evolution. By studying these phenomena, scientists can learn about the processes that drive planetary dynamos and the factors that contribute to the long-term stability of planetary magnetic fields. Long before telescopes, our ancestors wove myths around the night sky. Mercury, swift and elusive, captivated ancient civilizations. Babylonians linked Mercury to Nabu, god of wisdom and writing. Nabu, a scribe with a cuneiform tablet, symbolized knowledge. Greeks saw Mercury as Hermes, their messenger god. Hermes, with winged sandals, embodied speed and communication. Mercury, as Hermes, was a celestial intermediary. Beyond its mythological significance, Mercury's predictable movements across the sky made it a valuable tool for ancient astronomers, who meticulously tracked its progress to mark the passage of time and develop sophisticated calendars. By observing Mercury's cycles of appearance and disappearance, its conjunctions with other celestial bodies, and its position relative to the stars, ancient astronomers could predict astronomical events, such as eclipses, with remarkable accuracy. The ancient Egyptians, known for their precise astronomical observations and their intricate calendar system, incorporated Mercury's cycles into their understanding of time. They associated Mercury with Thoth, the god of wisdom, writing and timekeeping, further emphasizing the planet's role as a celestial chronometer. The Mayans too were keen observers of Mercury's movements, integrating their observations into their complex calendrical system. The Mayan calendar, a sophisticated system that tracked cycles of time spanning centuries, incorporated Mercury's synodic period, the time it takes for the planet to return to the same position relative to the Sun as seen from Earth, as a key element in their calculations. Mercury's unique properties, particularly its quicksilver nature and its association with the god Mercury, also made it a focal point in the ancient practice of alchemy, a precursor to modern chemistry that sought to transmute base metals into gold and discover the elixir of life. Alchemists viewed Mercury as a primordial substance, believing that it held the key to unlocking the secrets of matter and achieving spiritual enlightenment. In alchemical texts and illustrations, Mercury was often depicted as a serpent or a dragon, symbolizing its transformative power and its ability to unite opposites. Alchemists believed that by manipulating Mercury, they could harness its inherent energy to transmute base metals into gold, a process that mirrored their own spiritual transformation. Mercury's influence extended beyond alchemy, permeating the realm of astrology, a system of divination that seeks to understand human affairs and terrestrial events by studying the movements and relative positions of celestial objects. In astrology, Mercury is associated with communication, intellect, reason, adaptability, and travel. Mercury, the celestial messenger, has inspired art and literature for centuries. From ancient mosaics to Renaissance paintings, Mercury's image endures. Botticelli's The Birth of Venus features Mercury with winged sandals and caduceus. In literature, Mercury appears in Greek mythology and Shakespearean plays. His swiftness symbolizes urgency and movement. For centuries, our understanding of Mercury was limited to observations made from Earth, our view often obscured by the sun's glare and the limitations of early telescopes. However, the advent of space exploration in the 20th century ushered in a new era of discovery, allowing us to send robotic emissaries to this enigmatic world and unravel its secrets firsthand. The first spacecraft to visit Mercury, NASA's Mariner 10, made 3 close flybys of the planet in 1974 and 1975, capturing the first detailed images of its surface and providing tantalizing glimpses of its unique characteristics. Mariner 10's images revealed a heavily cratered world, resembling our own moon in appearance, but with subtle differences that hinted at a more complex geological history. Building on Mariner 10's pioneering mission, NASA's Messenger spacecraft embarked on an even more ambitious journey to Mercury in 2004. After a 7-year odyssey that involved multiple flybys of Earth, Venus, and Mercury itself, Messenger entered orbit around Mercury in 2011, becoming the first spacecraft to do so. From its vantage point in orbit around Mercury, Messenger revolutionized our understanding of this enigmatic world, beaming back a treasure trove of data that challenged long-held assumptions and revealed a planet far more dynamic and complex than previously imagined. Messenger's instruments peered beneath Mercury's surface, mapped its topography in unprecedented detail, and analyzed the composition of its thin atmosphere, providing scientists with a comprehensive view of this enigmatic world. One of Messenger's most significant discoveries was the confirmation of water ice lurking in permanently shadowed craters near Mercury's poles. This finding, which had been hinted at by earlier radar observations from Earth, surprised many scientists who had assumed that Mercury's proximity to the Sun would make it impossible for ice to survive on its surface. Messenger also revealed the presence of organic compounds, the building blocks of life as we know it, on Mercury's surface. These organic compounds, likely delivered to Mercury by comets and asteroids, highlight the interconnectedness of our solar system and the potential for the ingredients of life to be found in even the most seemingly inhospitable environments. Messenger's meticulous mapping of Mercury's surface revealed a world sculpted by a complex interplay of volcanic activity, impact cratering, and tectonic forces. The spacecraft's laser altimeter bounced billions of laser pulses off the planet's surface, creating a highly accurate topographic map that revealed the subtle variations in elevation across Mercury's landscape. These topographic maps showed that Mercury's surface is far from uniform, exhibiting a wide range of elevations, from deep impact basins to towering mountain ranges. The Clockwork Basin, one of the largest impact structures in the solar system, stretches across a significant portion of Mercury's surface, a testament to the violent collisions that shaped the early solar system. Messenger also discovered evidence of past volcanic activity on a global scale, suggesting that Mercury was once a much more volcanically active world than it is today. Vast plains of smooth volcanic material, likely formed by ancient lava flows, cover large portions of Mercury's surface, hinting at a time when molten rock surged from the planet's interior, reshaping its landscape. Mercury's eccentric orbit and its proximity to the Sun make it an ideal laboratory for studying the subtle effects of gravity, particularly the phenomenon known as general relativity, first proposed by Albert Einstein in the early 20th century. General relativity describes gravity not as a force, but as a curvature of spacetime caused by the presence of mass and energy. One of the key predictions of general relativity is that massive objects like the Sun should cause a slight warp in the fabric of spacetime, causing the paths of nearby objects like Mercury to deviate slightly from the paths predicted by Newtonian physics. This deviation, known as the precession of Mercury's perihelion, had been observed by astronomers for centuries, but its explanation remained elusive until Einstein's theory provided a framework for understanding the subtle interplay between gravity and the curvature of spacetime. While Mercury is the smallest planet in our solar system, its gravitational influence, though subtle, extends throughout the solar system, even influencing the orbit of our own planet, Earth. This influence, while minuscule compared to the gravitational pull of the Sun and the Moon, is nonetheless measurable and contributes to the complex dance of celestial bodies that governs the dynamics of our solar system. One way in which Mercury's gravity affects Earth's orbit is through a phenomenon known as orbital resonance. Orbital resonance occurs when two or more celestial bodies exert a regular periodic gravitational influence on each other, often due to their orbital periods being related by a ratio of small whole numbers. While Mercury and Earth are not in a direct orbital resonance, their gravitational interactions, along with those of the other planets in the solar system, contribute to slight variations in Earth's orbital parameters over long periods. These variations, though small, can influence Earth's climate and the timing of glacial cycles over tens of thousands to millions of years. The study of Mercury's orbit and its gravitational interactions with other celestial bodies provides valuable insights into the long-term stability and evolution of our solar system. By understanding the subtle gravitational dance between planets, astronomers can model the solar system's dynamics over vast stretches of time, tracing the paths of planets back to their formation billions of years ago, and projecting their movements far into the future. These models help astronomers understand the factors that contribute to the solar system's remarkable stability, as well as the potential for chaotic events such as planetary collisions or ejections to occur over astronomical timescales. Furthermore, by studying the effects of general relativity on Mercury's orbit, astronomers can test the limits of Einstein's theory and refine our understanding of gravity, one of the fundamental forces governing the universe. Section 6. Future Frontiers Beyond Messenger. While Messenger's mission came to an end in 2015 when the spacecraft, having exhausted its fuel, intentionally crashed into Mercury's surface, its legacy continues to inspire new missions and scientific inquiries. The data collected by Messenger has provided scientists with a wealth of information to analyze, leading to new discoveries and a deeper understanding of Mercury for years to come. But the exploration of Mercury is far from over. New missions are already being planned to build upon Messenger's discoveries and probe deeper into the mysteries of this enigmatic world. One such mission is Bepi Colombo, a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, which launched in 2018 and is scheduled to arrive at Mercury in 2025. Bepi Colombo consists of two spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, which will work in tandem to study Mercury's interior surface, exosphere and magnetic field in unprecedented detail. Section 1. Mercury's Enduring Allure. From a tiny point of light in the sun's glare to a world of surprising complexity, Mercury's journey has been one of revelation. Once a celestial messenger in myths, its movements tracked by ancient astronomers, it has become a scientific frontier, a laboratory for testing planetary theories. Messenger's mission reshaped our view, revealing a scarred, complex world. Its surface, a testament to bombardment, yet harboring ice in shadowed craters. A whisper of water in a world of fire. Beneath, a massive iron core churns, generating a magnetic field. These discoveries ignite our imaginations, reminding us the universe is full of surprises, waiting for us to explore. Mercury is more than just a fascinating object, it's a cosmic mirror, reflecting our planet's history and the processes shaping our solar system. By understanding how Mercury formed and evolved, we gain insights into the forces that shaped Earth billions of years ago. Mercury's magnetic field and water ice discoveries have profound implications. Did comets deliver water to Mercury and Earth, setting the stage for life? Our exploration of Mercury is a testament to humanity's relentless pursuit of knowledge, our drive to venture beyond the familiar and explore the unknown. It's a journey driven by curiosity, by the desire to understand our place in the cosmos, and by the recognition that the universe still holds countless secrets waiting to be uncovered. From the first crude telescopes pointed at the heavens to the sophisticated spacecraft we send to other worlds, our tools have evolved, but the spirit of exploration remains unchanged. We are explorers at heart, driven by the same wonder that compelled our ancestors to chart the stars and navigate by the constellations. And with each new discovery, with each image beamed back from a distant world, our perspective shifts, our understanding deepens, and we are humbled by the vastness and complexity of the universe we inhabit. The exploration of Mercury is not just about understanding a single planet. It's about pushing the boundaries of human knowledge, expanding our horizons, and inspiring future generations to continue the journey of discovery. As we look to the future of space exploration, Mercury beckons, its mysteries still unfolding before us. Bepi Colombo, with its two orbiters poised to unlock further secrets of Mercury's interior, surface and magnetic field, represents the next chapter in our ongoing exploration of this enigmatic world. And beyond Bepi Colombo, new missions are already being dreamt up, each designed to answer questions raised by previous explorations, each pushing the technological envelope further, each bringing us closer to a comprehensive understanding of this fascinating world. These future missions will delve deeper into the mysteries of Mercury's ice deposits, searching for clues about their origin and composition. They'll map the planet's magnetic field with unprecedented precision, revealing the intricate dance between its molten core and the solar wind. And they'll analyze the composition of Mercury's surface, searching for signs of past volcanic activity, and perhaps even hints of the processes that led to the formation of the planets themselves. The study of Mercury, a tiny world whipping around the sun at the edge of our perception, reminds us of our own place in the grand cosmic ballet. We are part of this intricate dance, our planet caught in the gravitational embrace of the sun, our destiny intertwined with the movements of celestial bodies, both near and far. As we continue to explore our solar system and beyond, we carry with us the lessons learned from Mercury, the importance of curiosity, the power of observation, and the humility to acknowledge that the universe still holds countless surprises. Mercury, the swift messenger, has delivered a profound message that the universe is a place of wonder, a tapestry woven from the threads of gravity, time, and the relentless dance of matter and energy. And we, the inheritors of this cosmic legacy, are privileged to witness its beauty, to unravel its secrets, and to share in the never-ending journey of exploration.